I think we're finally getting into the most fun part of today, the panel discussion. But unfortunately, we are like 30 minutes delayed. So we have a full house of control experts who are good at controlling dynamic systems under uncertainty, but not so much so in practice when it comes to time. So for that, I guess we're going to maybe just cut off some of the discussion. I have a list of questions that was connected from many of the NCCR students, researchers beforehand. So I'll probably just select some of the, the most intriguing ones that will hopefully also keep some of our invited speakers entertained. And yeah, I think we have the opera waiting for us next door, and I can literally see starving written on everyone's face. So I'm not going to keep this for very long, and also I don't want to keep our speakers keep starving then. So without further ado, so maybe I'll just first say that really thank you for all of our speakers for joining the panel. Right, we have Professor Tamer Basar from UIUC, Professor Lacra Pavel from University of Toronto, Professor Michael Muehlebach from Max Planck, and also Dr. Saverio Bolognani from ETH Zurich. All right. So I think the purpose of this discussion, this panel discussion, is really to, putting aside some of the technical details aside, because I know you guys already had too much of it. So we're going to really, as a community, a broader community, to think about and to, reflect on the past, the current, and also the future of dynamic system perspectives of algorithms, and hopefully try to also navigate some of the opportunities as well as challenges in this very active research area. So I'm going to start with, one of the most exciting questions that is going to try to unveil one of the biggest, mystery in this field is from a historic perspective, as we see that dynamic system perspectives has been constantly used to help us to analyze algorithms. And today we already see also lots of recent advances on this topic. So from your perspective, do you think this is the golden age, or this is another hyped cycle of this field, and why so? Yeah. So based on the ETH tradition, so I'm going to take answers according to your geographic distance to ETH. So that being said, I think if I'm correct, then Tamer is going to be the first one.
I see.
Yeah.
What's the difference between Toronto and yeah.
So,
well, it's I wouldn't. Oh yeah, here's. The question says, is this the golden age? I would say, I would replace the with a. Is this a golden age? Because there are multiple golden ages, and the algorithms, using algorithms, has been an integral part of control theory research. Leaving aside game theory, which is at its peak and still growing, and definitely the algorithms are important part of game theoretic sort of analysis, because different players interact with each other, respond to each other, and so on. So that's a natural occurrence. But if you go back to even to 1950s, to the time of, say, even dynamic programming. Dynamic programming itself is an algorithm. And so what Bellman came up with in solving dynamic optimization problems definitely is something which we have taken for granted, maybe didn't look at it from an algorithmic point of view, but it definitely is. And so moving all along, and the adaptive control in the 1970s, and definitely was very much algorithmic, and very much, there was very much learning involved in that. And we are actually rediscovering some of the adaptive control techniques and methods of so there is always what I'm really worried about is rediscovering things. So for that reason, it is always beneficial, especially to the young generation, to not only look at what has been done during this decade, but also go back and see what lines of thinking were at 30 years ago, 40 years ago, and so on. And there is, it's not a futile effort to dig out what has been done. So algorithms have been all along, I think, part of control theory, and maybe not seen that way as we see with bringing in machine learning and so on into our sort of portfolio. But also it paralleled the improvement in computational techniques and computing power that has driven some of this research. So it's not in isolation. Definitely, there are other discoveries or other advancements which have had input into this algorithmic development that we see today. But definitely, I know in the aerospace industry in the 1950s, in the 1960s, Bryson, for example, was always interested in developing algorithms for dynamic programming or for trajectory optimization and so on. So anyway, I'll stop here.
Thank you. Yes, that's a very interesting point. Yeah.
So I'm going to speak from my own perspective, which is starting to working in this area from about 20 years ago. Yeah. So Tamer has the experience and the knowledge to actually bring it way back. But I can tell you that speaking from the perspective of looking at these problems within the control community, when I started, I was telling yesterday to Tamer, as a control theorist working in game theoretical problems, we were just a handful of people meeting at conferences, remember, with Tansu, with Jeff Sharma, with just maybe Angelia, yeah? And now seeing nowadays...
But even 10 years prior to that,
there
was almost nothing. I
Exactly,
mean,
so that's why I'm saying...
I was the loner.
Yeah, that's why I'm saying that you have, I'm speaking from the close to mid-2000, to 2004 or so. So... to see what's become now that, at least game theory, optimization, algorithms, it's everywhere in a control conference, in CDC, in ACC. I mean, you have session after session after session. To me, it's excellent because 15 years ago, I used to have a discussion with Bruce Francis in his office, and he would say, it wasn't a mainstream. He would say, oh, but what's your plant? You don't have any plant. So it's not controlled. So this wasn't traditional mainstream control area. So from that perspective, I think there's been a convergence of both tools, a mindset of the people that changed, realizing that algorithms, hey, you do have some systems in there that you have to deal with. Also the tools, the mathematical tools, because that time there wasn't, for example, this equilibrium independent passivity, there wasn't invented yet. Yeah. So from my perspective, I think that's it's really a golden age. I'd hope it's not a hype, but again, I'm very happy. To me, this is personally the most exciting thing, to see that there are so many people in the control community bringing together and working on this. Yeah, so I'm going to pass it to Michael.
Thank you. I don't know if I can add so much, but I think So you asked if it's a golden age or a cycle, but I think science happens in cycles, and it's not actually a bad thing. And I think this is the way science is done. And every cycle we discover something new.
I just wanted to add, of course, a much narrower perspective on this thing. If a good test, right, to tell if maybe if something is, let's say the following: like it used to be that to propose a algorithmic or computational way to control problems, like there was an effort to convince, right, so some application domains, right, this was a good idea. The motivation that at least I personally see behind this analysis of algorithms as dynamical systems is that they are being used as dynamical systems. So they're being used with streaming data, and they're being used in close loop with physical systems. So instead of, I think this makes it a good problem. Like when the problem is there, even if you're not working on that, like in the sense that it's not connected to your way of solving it, but the problem is there, and they are going to do it no matter what to connect algorithms and physical systems. And there's a need for an answer to some questions. I think this makes it a problem that has the chances to survive longer, right, and to be more impactful. And it seems to me that at least for the application domains that I've in mind, this is happening. There is a need to understand algorithms when used in real time or when used with streaming data, and when they need to be interpreted as feedback systems. So I consider this a good sign.
Yeah, great. Thank you for all of that very valuable insights. And just to follow up on that, right? So, of course, it's very important to understand always algorithms, whether they're continuous time or discrete time, to understand their robustness, convergence, implicit bias, so on and so forth. But there have been also many other analytic tools exist in the literature, right? Say, for instance, speaking of these variational inequalities with monotone operators, there are other tools that we can analyze them, or with Nesrov's acceleration, as like Michael talked about, right? There are all kinds of other interpretations exist as well, right? So what would you say is the unique strengths or attractive points of using this system theory perspective? And also, what would you say are the limitations and challenges? Yeah. So now we're going to be,
Same?
Sure, we can go with the same order. Yeah.
Well, I would say the feedback is unique to control, to the control community, and every algorithm definitely has a feedback structure. So from that point of view, it's control. People who are trained in control have a lot to contribute. And I made a remark earlier. I asked the question of whether memory was used in these algorithms. Well, someone who is coming from outside control would never think of using integral feedback, for example. Integral feedback is using memory. And we know that using integral feedback, you can make a system more robust, you can ensure stability, and so therefore this is something that only someone who has a control experience can bring into these algorithms. So the dynamic systems viewpoint is not something that the standard optimization or machine learning people would approach the problem as. So.
Yeah, I completely agree, and it's the systemic viewpoint that really is the key differentiator, and the fact that we're always looking for insights, for genericity of a property, and this translates in intuition into what's happening behind. You mentioned variational inequality operator theory. I've worked on those, and I'm working on those too. But the insight comes always from the system theoretic side of things. Yeah, it's some of those partial information algorithms Giuseppe is familiar with we've approached them in a operator theoretic perspective for generalized Nash equilibria. But to get to that point, it was from a system theoretic that we got the insight. So, because if you're just, at least this is my experience, if you're just following one of those optimization, operation theoretic, you don't get that insight. You don't necessarily have the intuition of what's happening. And to me, this always has been the big advantage of having a system theoretic perspective.
Yeah, I very much resonate with this. I think the systems theoretic point of view gives you a more qualitative understanding of certain things and allows you to apply your methods also if the underlying assumptions are maybe not strictly satisfied. But at the same time, I think as a control person, we should also look at what computer scientists are doing, and they also have very interesting problems, and they're also sometimes very good at other things, so discrete structures or understanding scaling with dimensions and things like that. So a lot of stuff which maybe we're missing on the control side of things. So I think it would be fruitful to go from both sides. Yes.
I would just add that apart from the methods, right, that could actually come from new methods probably bring new results. But also some problem statements could benefit from the control theory perspective, right? So, for example, the question I received about the effect of noise on the outcome of a running algorithm is not super traditional in optimization or computer science because you're fed with data or you have an episodic nature of your algorithm. And sure, there's definitely some work there, but it's not the first thing I will look at. Same thing like, are you concerned about the rate of convergence in the worst case, or are you looking instead at whether there's input to output stability from uncertainty in your data to your decision, right? I think that also the problem statement could benefit, or some problem statements could benefit from this perspective.
Right. Great, I completely agree. And now I'm going to give you the hard one, right? So you have talked about all of these benefits of using this system theory perspective. But on the other hand, many other research communities like machine learning, in industry, they are increasingly making use of black box optimization algorithms and computational methods. So does these other research communities and industry really care about what we're doing here, and what do we need to bring to the table so that they do? So now maybe we'll go to the reverse of the order.
Okay, so I can't, of course, my sampling of what industry thinks of different methods is pretty limited, but if there's solutions, or at least that would be my take on this, like if there's solutions, that black box solution that make some industry in some domain happy, fine, right? I mean, I'm sure there's problems where that's not, where those kind of methods do the job, right? There's other methods where, or the other problems where you need to provide some transparency what you're doing, or you need to provide some guarantees on what you're going to achieve, or you need to design things in a way that are guaranteed to work even if the system splits in two, right? This is I don't think there's just a few of them. I think there's plenty of problems where you really need to derive solutions which are not black box, and I'm not particularly disappointed that some applications can be solved with black box solution, and that's also fine, right?
Yes, so I think the industry definitely cares. So I was at Berkeley, and we had collaborations between different groups, and this was funded also by industry partners like Google and Alibaba, and we had yearly meetings, and I felt there was a lot of interest also in this sort of fundamental and abstract research. And then I also met people from the finance industry who are very interested as well. So I think there's plenty of interest.
And getting to the other fields you are mentioning, like computer science, and there's nothing to say that different approaches don't work. They bring in a different perspective, and that's all the better, I would say. I mean, this is what's advancing the science and the innovation. If you get people from different communities bringing and shedding a little bit of light on the same problem. Yeah? So I'd say we shouldn't regard ourselves as being the authority or the ones that are the only ones, or they shouldn't. I mean, each community, I think, brings their own perspective on things.
Yes, there's a lot of benefit in, I agree, bringing different communities together. And the conferences are actually doing that. I mean, you go to a machine learning conference, you see many control people, you see many computer science people who know nothing about control, but they seem to have, 10 years ago, they wouldn't have any common language, but now they do. And so even to CDC, if you look at the sort of the program of the last 2 or 3 years as compared with 25, 30 years ago, you cannot say that it's the same conference. So, and it does attract, you look at the affiliations of people and their backgrounds, it does attract people from other communities as well. So I think many have realized that bringing different people to the table with their own tools, but having some overlap and being able to communicate with each other is of benefit to all these communities. And so I would say that the portfolio of control has expanded substantially and significantly. And I mentioned CDC as one sort of evidence of that, and definitely the control journals, the transactions, it's the same thing. You pick up a copy of the transactions of Automatica today and compare it with what it was 25, 30 years ago. You cannot say that it's the same journal. So it is, there's a lot of, I mean, I see that at Illinois also, I interact with colleagues with different backgrounds from different departments, and that definitely provides value added to all sides, and the students benefit from that as well.
Great. So if we're going to look forward, right? So then what would you say is the biggest challenge in front of us, and how would we push this whole research field to a next level? And and where do you see us like in 10 years? Just as a final question, and then I will open the floor to the audience here. Yeah.
Well, it's difficult to predict definitely these things, and that's why I say that the 12-year sort of commitment that the Swiss National Science Foundation has decided to provide to researchers is a perfect thing, because you cannot predict what you can do in 5 years or even 10 years from now. So it should be a free sort of without any constraints. You should look at the natural flow, which is driven by curiosity of individuals, and what the needs in industry and in social sort of infrastructures would require, and things would change, and the climate, of course, is an important thing, and I think the control theorists will have an important role to play in environmentally making environments much more friendly, and all kinds of sort of pollution control and so on. So all of these are feedback systems, and there's definitely a lot of modeling that needs to be done, and a lot of learning within the modeling or partial modeling framework that needs to be done. So I see the future quite bright. It's not, you cannot say that it's going to be the end of the road. It's actually the road branches out in many different directions, and people will move in different directions, and that's a sign of health.
Yeah, so I agree. It's really difficult to predict where we'll be in 10 years. I mean, compared to where we were 10 years ago. And there's so many other things aside from the curiosity, cross-fertilization between fields. Yeah, so problems that maybe we didn't even think nowadays. Yeah, they're going to come and they're going to require our approach. So as long as we keep our interest bright and open to cross-fertilization with other fields, I think we're in good shape. Yeah.
I also think technology will also drives a lot of interesting research. So we're going to have more and more compute, more and more data. We're going to have more and more interesting sensing, interesting actuation, and so on. So there's a lot of interesting challenges coming up. Also, partly from a practical point of view, but also theoretical nature. Yeah.
Yeah, I can only just mention one thing that I found a bit interesting is that I don't know. I have the impression, at least from my perspective, that people working in control were a little bit exempt from justifying what they were doing in front of society, like compared to someone working in medical science, right? Or it seems that automation is becoming something much more discussed in the public as well, which might actually be an interesting new dimension, right? That sometimes when you take a decision or design something, you need to also explain whether, why it's working, how it's working, or if it's a good idea to do it or not, right? Until now, there was part of the research was a little bit of puzzle solving, in the sense that once you solve it, people will trust you as an expert, and you don't need to explain it to anybody. Right, and I think this could be an interesting dimension in the future.
All right, thank you very much for all of this wonderful feedback. And now you are going to just open the floor for all of you here. So this is the best time that if you want to challenge our invited speakers here, just raise up your hand, and then we'll bring you the mic. Yeah.
I have a very quick one, and you're only allowed to answer with a single word. Namely, I realized a common denominator across all slides was that we like to think in the world of block diagrams. So is there any sort of cool algorithm out there which you wish you were able to explain and analyze by means of a block diagram? Single word answer.
First, proximal algorithm.
Any order. All right, we can also follow up after the ranks.
No. We won't let you go unless you told us the answer after the trip. Yeah. So, any other questions? Yes.
So I was almost surprised to not hear more reference to the obvious 2D, so deep networks and data. Do you think this field is going to go more into that direction as well? I mean, you were talking about policy optimization. Most of the people that do policy optimization do it with a deep network. You were talking about SGD. Most people that do stochastic gradient descent do it on deep networks. So, and there's always a lot of data involved. So what's your prediction how this story is going to merge into your field or less?
Anything that's not built on concrete foundations is apt to fail. I mean, at this point, the deep networks is very ad hoc from what I see, and so unless someone or some group puts it on some concrete basis, I think it's not going to be something that people can rely upon. I mean, you could have success stories in playing the best chess or all kinds of games and so on, and lots of trial and error. And but are there any guarantees that one can provide? So until that is established, then I wouldn't put my bets on it. That's my opinion.
Yeah, thank you. I'll add that it's not only the performance guarantees, it's the answer to the question why. Why does it work? Can you provide some intuition? So as long as that answer doesn't exist, I'd say that it's hard to be accepted and to actually convince. Yeah, so there's going to be indeed some success stories, but what about the power of generality? Is this going to hold? Yeah, so I'm skeptical. Yeah, let's just say.
So I want to contradict maybe the old generation, and I will say, I'm sorry, I mean, but maybe I should rephrase it as deep. So I don't like this deep necessarily, but I think it's a matter of having more and more compute, and I hope that controls would embrace the possibilities that arise with more and more compute, and I wish we would do that. Yes.
I would just report a personal bias, which I think and a lot of people in control theory share, is that there's a general, I am personally intrigued by understanding how things work, and by, solving taking a problem and removing all the unnecessary pieces until what I see is almost like a puzzle, and it works, and it's elegant in the way it works. And this is taken away by in some approaches. So there's not a judgment from my side on whether they might actually work and do the job, but just it's not as intriguing to study from my point of view. So I just make it personal.
If I could add. So I think Michael here is actually the one that's closest to maybe where we should be in terms of that cross-fertilization, yeah, because people from computer science or whatever, they're much more open, and maybe we should ourselves be a little bit more open to that, but it will have to actually alleviate our concerns. I mean, you've seen it's not only a generational, I think it's more of a community mindset that we as control theorists, we tend to want to understand why things are the way they are. Sure. Yeah.
Sure. And I have also these concerns, of course. But at the same time, we shouldn't close our eyes to the possibilities, I think.
Yeah.
Wonderful. So I have a question to Tamer. You said control theory and algorithms will play an important role in solving environmental and pollution problems. Can you elaborate a little bit on that? And would you say that this sort of signifies algorithms moving from the computer to the real world?
Well, the reason why I said that is because the environment itself is a feedback system, and control people have a lot of experience in dealing with feedback systems, and so you can use the feedback loop in a way such that the output is going to will track the desired trajectory. And so for the environment, of course, we have different trade-offs, and then we have to see what the ultimate goal is, both in the short term as well as the long term. And as long as you can design the feedback loop in a proper way, then you can reach those goals.
Good. Any other specific questions? Okay.
No, it's getting back to actually Niao's question about where's the future going. And there was a lot of talk about cross-fertilization and bridging between areas and so on and so forth. I guess it's a standard question, but are we equipped to do this? I'm thinking more of our educational activities. We're all academics. And is the curriculum that we're developing up to the challenge? At least here, a lot of the discussion is disciplinary in the strong fundamentals that we need. There's not a lot on continuing education. There's not a lot of interdisciplinary subjects. So from an education perspective, where should we be moving?
There's it's a deep question, and academics and universities all over the world are actually struggling with that. You have, of course, the amount of knowledge that students should acquire is growing. So you have to be very selective. And you have only 4 years graduation. I mean, at Illinois, we had talked about maybe a 5-year thing, but they said, no, the parents are going to revolt because who's going to pay tuition for 5 years? 25% increase. So you have to fit whatever you want to teach into 4 years, and you have to be selective. And there have been quite a number of sort of experiments in going in removing these disciplinary boundaries and have a common sort of or a very flexible, say, an engineering program, but not many of them actually. I'm not aware of any that has been successful, and they went back to the disciplinary. I personally think that even though it's rooted so far in the 1940s or 50s, still the current disciplinary sort of boundaries are the right ones. But you should bring in flexibility for students to cross these boundaries and to take additional courses depending on what they would need. And we should also, within electrical engineering or computer engineering or mechanical engineering and so on, and try to modernize our courses so that the students would be in a much better position after they graduate, either to make contributions in industry or move on to further PhD or higher degrees. So it is, I think, within the given system, as long as you have the flexibility and as long as you can always update the contents of your courses, which we always do, and bring in, I mean, we do have machine learning courses that students are taking now in the program, which we didn't have 10 years ago, so even 5 years ago. So there is a natural sort of a tendency to modernize and make it more up to date, but I don't think it should be evolutionary and not revolutionary.
I think it depends a lot on the constraints. At U of T, there's the 2-year curriculum that's fixed, it's set, there's nothing. And then in the last 2 years, you have some flexibility, and there has been some adjustment in the sense that there were optional courses that were just outdated, physics-based, for example, that were replaced with machine learning, options that were created, machine intelligence, and that actually opened more students' eyes to the control, because the control courses were actually feeding into those. Yeah, there isn't as much, for example, at U of T, they're not taking an optimization course until a graduate course. Yes, so they're doing machine learning, but they're not taking optimization course. Yes, so I think this is, in my opinion, something that it's lacking. Yeah. Now I can speak of, from my experience, undergrad in Romania, where I think the advantage was the fact that we had curriculum more on automation and computers, as opposed to all electrical and computer engineering. So we were more targeted. I did optimization as an undergrad. Yeah. Here they don't have the place. They simply don't have the place. Yeah, there are some, and this is what's good, but it's within the constraints.
At Illinois, we do
You
have
do?
an undergraduate.
Yeah.
I think this is also a very question for maybe more suited to more senior people. But I think you should also maybe not neglect that. Or the question is, what would you like to achieve? Would you like to educate good researchers? Would you like to educate people that go to industry and solve problems there? And I think if you want to have people that do great things in industry, then I guess a classical way of thinking and having mechanical engineering, electrical engineering that have well-defined competences is something that's useful for industry. Now, for doing good research, I think it's maybe more interesting to have some sort of slack or where you can change disciplines.
Yeah, what I can say is I can imagine a little bit of contamination of the control curriculum by something new. Like when I learned, I think the very first block diagrams I drew, like with a feedback system, was starting from an analog circuit and make it into, from Kirchhoff equations, you get a block diagram that you can study. I think it's fair to maybe revisit what a controller is, in the sense that, when teach control to students, controller used to be, even maybe an analog circuit, maybe a microcontroller, maybe something more. And now it could be that it includes algorithms, or it includes something beyond what we are used to. I think it's fine if there's some contamination to expose the student. I mean, what we have seen today, there were pieces here and there that one could reassemble or use in a course, like teaching how interpret some optimization algorithms that eventually might run into a controller and show that they're acting closely with a system, or showing why they converge. I think it was something like so far beyond that you could not explain it in a control course. But of course, I mean, when you push something in, something comes out, right? So.
Good. I was just told that the apero is ready at 7, so I think we're right on time. So just maybe to wrap it up, you're all convinced that this is a golden age for us to do research in systems, and there are, of course, a lot of open challenges on the theoretical side, the practical side, the educational side, the environmental side, right? So this is definitely your moment to shine. So just jump on it. And for that, I'd like to really thank all of our speakers today, and also big thank you to all of the audience for bringing up so many interesting questions, and also the whole NCCR crew for making this event happen. And I think we all deserve a celebration, and please join us for the apero, and see you there. Yeah.